Sinusoidal waves or sine waves. That's what we call the representation of the current that happens in our AC current in our power distribution. And in the United States, the one cycle of power happens every 1/60th of a second, or 60 times a second. And what it does is our current in your household wiring has a zero current flow. Then it's going to ramp up in one direction till it hits a maximum current flow, ramp back down to zero, and then it's going to ramp up in the other direction to its peak current flow, and then back down to zero. One complete cycle, 1/60th of a second. That's called a sine wave. Here in the United States, this happens again 60 times a second, and that's called 60 hertz. And these are created by alternating current generators, which we refer to as the alternators, and those are inside of our power generating plants. Let's take a look at this simplified diagram and picture that it's in a wind turbine. And we have our blades are connected to this armature, and it's spinning this armature of coiled up wires through the magnetic fields here. So this is a pretty simple representation, but when the wires on this coil are not cutting through the lines of force, which is represented right here, it's at its lowest, which is zero current flow. As it begins to rotate up in this direction, those coils of wire begin to cut through those magnetic lines of force, and as they get to that 90-degree point, they're at their most, they're at the peak of current flow, and then as they continue through these magnetic lines of force and somewhat dip back out of them, they're back down to zero, and then this armature hits the southern pole, which pushes the electrons in a different direction, and it continues this cycle of the peaks here and the valleys and the peaks 60 times a second, and that's one complete cycle. Maximum voltage is at 90 and 270 degrees. And again, here's another illustration of that where the armature isn't cutting any lines of force, and as it goes through and hits the 90-degree point, it peaks out up here at the top. Now this is a familiar AC power distribution diagram that we have seen before. And again, I want you to remember that inside of our generating station, huge AC generators are spinning around inside of magnetic fields of force, and it's causing that current to flow back and forth 60 times a second all the way down to our residential home. And if you think about this, we have spinning armatures inside a magnetic field of force that are being spun by wind or water or steam, whatever the case may be, pushing electrons back and forth. It comes down here to the motor in your air conditioning, and now it takes those magnetic fields of force and it recreates that rotation over here in your home to spin the motor. Pretty ingenious, and if you think about it, I can't even imagine Edison or Tesla that came up with this idea. Now, by the time the power gets to your home, you're familiar with seeing the transformers up here, which always blow up. The voltage coming in on the high voltage wires is up there about 4,800 volts, and it's not, depending on your power company, but it is up there in the thousands of volts. And what they have is a step down transformer that takes that 4,800 volts and steps it down to 240 volts here. They center tap it for the neutral, and this is connected to some copper piping that goes into the ground, or a copper rod that's driven into the ground. And on one side of the transformer it is 120 volts, and on the other side of the transformer it is the opposite polarity of 120 volts. We'll go into this a little bit more later. For a total between these two legs of 240 volts. Almost all U.S. households that I'm aware of have 240 volts input coming in from the transformer out in the pole or in the ground or on the ground next to the home. That's called the Edison hookup that does that. So coming from the transformer outside of your home, we have those two lines that come in here with 240 volts AC coming in on those two lines through the main circuit breaker right here. So here is a little diagram of what happens inside your home. So we have our 240 volts AC coming in on the two lines, L1 and L2. That's a typical designator for our line voltage coming in, which is L1 and L2. It's 120 volts on L1 and 120 volts on L2 for a total of 240 volts. So L1 comes in, goes through that main breaker, it comes over here and goes down a bus bar inside of your circuit breaker panel, and then you have circuit breakers which power your, this would be for your bathroom lights, this would be for your kitchen lights, this would be for your living room lights, and so on and so forth. Same thing on the other side here. And then for our 240 volt circuits for our air conditioning condensing unit, electric water heater, if you have an electric furnace, that's what these power. So it takes the L1 leg into a dual breaker, and it takes the L2 leg into the other side of the dual breaker, so you have a 240 volt branch output right here. And then you have one circuit breaker for each one of those 240 volt appliances. But we're interested mainly in air conditioning and heating, so let's take a look at this. Let us assume that this circuit breaker right here is our outdoor condensing unit circuit breaker, and it's feeding a branch circuit to the outdoor condensing unit. So here we come into the condensing unit disconnect box, which is right here, coming from that 240 volt circuit breaker that we just took a look at. Sometimes these disconnects have fuses in them, and sometimes they don't. So it just depends on the age and the installation and the different codes in the different cities and states. So they always come into a disconnect, whether it be a fuse disconnect or just a service disconnect, so that you can disable power while you're working on the system. You don't have to do a lockout tagout, and you have control over the power coming into the... Alright, so we are now taking that power from that 240 volt circuit breaker that was in the panel, which is from the garage or the house or wherever it is, and it comes out through the field wiring into the disconnect box. This diagram shows a fuse disconnect box with 230 amp fuses, and that's usually located right here at the condensing unit. Many homes don't have a fuse disconnect box. It depends on the age of the home and also the codes for the city and the state that you're working in. So this can either be fused or unfused, but it's always a disconnect box that you can use to disconnect the power so that it's safe while you're working on it. You don't have to do a tag out lockout, because if you turn the circuit breaker off inside the house and then you're working on it and the homeowner comes out and turns it on, you get zapped. So this disconnect protects you here so that doesn't happen. The other thing, I always recommend that you check once you turn off the circuit breaker or pull that disconnect that there is no voltage present at the unit, because I have seen more than once systems that have been hardwired behind that panel that you can't see that bypass those fuses or that disconnect. So make sure that you stay safe when you do that. Our 240 volt power then comes into the condensing unit outside, and it goes in through a transformer, step down transformer, to give you your control voltage for your thermostat, and then it goes up here to power the different loads within the home. We'll get into some more schematic diagrams later, but that is how we get the power from the power generating plant through the power distribution system, through the home's power distribution system, out to the air conditioning condensing unit. All right, so we'll talk about a little bit more about these schematics and these types of circuits in later lessons. So this is just a very simplified one, but you just need to understand how that power gets to the unit.